לא, המצלמה עובדת,
היא לא עובדת, הוא ביטה אותה עכשיו.
אבל תראה,
הוא ביטה
מסתכלת
אותה עכשיו.
עליי.
חכה, חכה, היא...
אחת
ברגע ש...
שתיים.
רק שנייה. עכשיו תראי נקבעת. 1-2 עכשיו. הנה, אתה רואה
או,
מתמקדת. עכשיו צריכים את זה. יפה. בוא נחשוב שני טעינות ככה כשהיו.
הוא לא טוען בגלל.
טוען, טוען, יש לו איפה...
כן, אבל פעם אחת הוא מת. אולי הוא טוען דרך טלפון מספיק, אני לא יודע. אני חושב, זה ש... בגלל זה, אני לא יודע. כן, אבל פעם אחת קבלתי רק על זה, ואז באמצע השיעור פתאום. יכול להיות או שאני חושב שהיא לא יודעה לקבל מכאן, או שהוא יודע אבל לא בהספק מספיק.
המציאות האלה יש לך, אני חושב יותר יש לנו קובל ב-USB-C, הבנתי. או איזה דק מישהו כבר, או שיש פה טעינה? יש טעינה? לא, אין.
לא, יש.
כן, תחליף מחשב, שמע, מחשב ישן.
זה לא עכשיו, מה זה שנתיים.
לא שנתיים, זה לפני 2018 זה עשו.
לא, לא, לא מזמן.
אני אגיד לך מתי פעמים. תראה לי מה המספר שלו. בעיקר? מה רשום בעיקר? אתה רואה?
זה לא נוגע זה?
1, 2, 3. נסימתה.
לא, יש לך איזושהי... טוב, נראה כמה הוא באמת, ואם הוא אמר שלא יכולים לעשות.
בהצלחה.
תודה.
היום.
אז אני קודם כל אחזיר את החובות שיש לי הרבה. אני אגמור לדבר על שיפים ואני אדבר על הקושאות של קופואידים שאני חשבתי לכם הרבה זמן. אני מקווה שאני אעשה את זה קוהרנטית. ואז הבנתי שבעצם הקטגוריות מונואידליות זה די מצדיק קורס משלו. זה נושא ממש מגניב. אני בעצם ידעתי את זה כי הייתי פעם בקורס בקטגוריות מונואידליות, שזה מילה סמסטר, אז זה לא צריך להפתיע אותי שיש מקום בסמסטר לנושא. אבל זה באמת ממש מגניב. אז אני כנראה נקדיש לזה עוד 2 הרצאות ואני אנסה לספר. אני לא אכנס להרבה פרטים, אבל יש מלא דברים מעניינים כדי להכיר. בסך הכל לא מאוד מפתיע, כן? כי אם תורת קטגוריות זה קטגוריפיקציה של תורת הקבוצות, אז קטגוריות מונואידליות זה קטגוריפיקציה של תורת החבורות, לא יודעים, שברור שהיא הרבה יותר עשירה, כן? וכן, אפשר לחשוב על קטגוריות מונואידליות כמקרה פרטי של 2 קטגוריות, בדיוק כמו שאפשר לחשוב על מונואיד כמקרה פרטי של קטגוריה, אבל יש הרבה עיסוק ממש בו, כן?
אנחנו השתמשנו בשיפט ספציפי במקרה של כאילו אופן סט של איזשהו טופולוגיה, אבל יש, אני מניח גם את ההגדרה הכללית מעניינת, כאילו כשמסתכל.
מה זה ההגדרה הכללית? יש הכללה של מושג שיפ, ההגדרה המקורית של מושג שיפ.
זה כמו שפרי שיפט, כאילו קל להגיד אותו כי זה פשוט מ-C-op ל-D.
אבל זה נכון, נגיד את זה ככה. היסטורית היו מושגים שיף ופרי שיף. הם בעצם כנראה מושג שיף היה לפני פרי שיף. זה הייתה ההגדרה של הרי, אז לא תמיד שיש לו מושג שיף. ואז די הרבה שנים אחרי, באופן טבעי שאפשר להכליל מושג השיפ לדברים שאינם אחרים טופולוגיים. ולא לקטגוריות באשראים, אבל לקטגוריות מבני מסע. וזה מה שקרה באופן טופולוגי או באופן טקסאי, ועל אובייקט מהסוג הזה, ויש מושג של שיף. ואז, וגם עובר דרך הגדרה של פרש, מושג של גודליק, ובמושג של פרש אפשר להתחיל לכל גיל, זה פשוט ורבנטים עובד לכל קטגוריה. אז כן, יש מושג של שיף על סייט, אנחנו... זה אחד הפרקים האופציונליים, אני לא יודע אם נגיע לתקווי במדבר על קטגוריות מונידליות, אולי בכל מקרה אני אשאיר את ההרצאה האחרונה על איזה עוד דברים יש לו.
זה בין המקרים לא יודע אם יחידים, אבל שלא הלכנו להגדרה הכללית, ואז ראינו את המקרה הפרטי, ראינו רק את המקרה הפרטי.
כן, מה זה הגדרה כללית? כל הדברים האלה שאני מפתח, יש נושאים יותר ויותר כלליים שמכניסים את...
כן, אבל...
גם את המושג פרשיפ, גם את המושג שיפ, או פשוט רגע על הקורסים דברים. היסטוריות שיפים ופרשיפים הם מכונים קולוגיים.
גם כשהסתכלתי באין לעבוד, זה באמת ההגדרה הכללית, זה עם שמות של שאולים טופולוגיים, כאילו סייטים וכל דברים. לא יודע אם סייט.
סייט לא שואל, סייט זה כאילו, הוא נשמע דומה למרחב, כן? והרעיון שזה הדבר שמחליף מרחב טופולוגי. וקאברינג זה טופולוגי. העבוד שבמרחב טופולוגי היה קאבר ברור מהגדרה. הסיבה לזה המוטיבציה המרכזית זה גיאומטריה גבט. גיאומטריה גבט לכאורה יש טופולוגיה. אבל אם אתה מנסה לחשוב על זה כמרחב טופולוגי ולחשוב על טופולוגיה גבט, הוא לא יזכור את הגוש. היא לא נועדה לזה, כן? היא נועדה בשביל להדביק את הדברים וכו', אבל היא לא נועדה לחקור את הגיאומטריה של המרחב. ועדיין, המידע הגברי מספיק כדי לקבל לא את כל המידע הטופולוגי על המרחב, אבל הרבה. זאת אומרת, אם יש לך יריעה גברית שמוגדרת מה המורכבים, אז אתה יכול, אם אתה אומר, אני לא יודע שזה המורכבים, קחתי סתם סדר, יש המון סדרות סמורפי בסימפל. בוא נראה אם אני יכול לשחזר את הטופולוגיה של המרחב, פשוט מעצם זה של הפוליטי. זו שאלה קונקרטית, אני יכול לשאול כזאת שאלה, אם יש לך יריעה שמוגדרת מורכבים, עם כל מיני מקדמים שהם דברים מורכבים, פאי, מה שלך, ואז אתה לוקח אוטומורפיזם של זה. למשל, שמחליף את פאי בית. האם, יש לי אפשרית, עכשיו אומרים עם פאי וליטי מגיע כן, מחליפים את פאי וליטי. האם תהיה מיומורפית ליריעה מקורית? והתשובה היא לא. אבל היא מאוד לא רחוקה. אבל רוב האינווריאנטים של טופולוגיה גבט, אתה יכול לשחזר בלי לדעת. זה טופולוגיה בפרט בצורה שתהיה אינווריאנטית. אתה לא יכול לחשב את התחבורה היסודית, כי התחבורה היסודית יכולה להיות שונה, אבל אתה כן יכול לחשב את כל החבורות ההומולוגיות, ואתה יכול לחשב את ההאשמה התורספית של התחבורה. בדיוק מאוד גדול אתה יכול לחשב את הטופולוגיה, ואז יש דרך מה לעשות את זה בלי לדעת את הטופולוגיה של C, שתעבוד מהשדה כללי, ואפילו צד חיובי. או מכבי יותר מצוינים. ובשביל זה צריך את הטופולוגיה שלנו. אפשר להתאים לזה קטגוריה, יש סייט, שההומולוגיות שלו באמת יש טופולוגיה את ההומולוגיות שלו. כי בעצם, מה הבעיה המרכזית בטופולוגיה זריצקי? זה שאין בה את משפט הפונקציה סתומית. אם יש לך הנקל, לא יודע, Z בריבוע, מ-T-star ל-C-star, זה הנקל דיפרנציאל של האפים, או יכתב יכול להיות פתיחה המקומית, בעולם של טופולוגיה דיפרנציאלית תהיה פתיחה המקומית. זה ברור מה שאני אומר או שלא? כן. אתה רוצה לפתור את משוואה, זה בריבוע של...
כן.
ואתה יכול, כאמור, אתה מסוגל לפתור אותה מקומית באופן לא סתם זה שיש לו שתי דיפרנות, אלא שאם יש, רוצה ממש טוב נוסחה, שורש, כן? אין פונקציה גלובלית שורש X, זה לא מצפה שתהיה פונקציה גלובלית שורש X, אבל בעולם של טופולוגיה דיפרנציאלית, אם נצביע על הדקה מישור מורכב לעצמו, אז בכל נקודה יש סביבה ששם יש לה דקה חלקה נקודה שורש X. הסביבה יכולה להיות מאוד גדולה, והיא לא יכולה להיות כל המישור, כן? והיא לא יכולה להיות קבוצה חדרית, אפשר לקרוא כך, מה נקצור? קבוצה חדרית, זה משלים כמספר ספרי של נקודות, זה גדול מדי. ובהרבה מובנים זאת הבעיה היחידה, ברגע שאתה פותר אותה, אז אז פתרתי את כל נושא הטופולוגיה שלו. אז הטופולוגיה זה כבר לא טופולוגיה זריצקי, אבל ברגע שפתרת אותה אז הכל בסדר, כן? אז בגדול מכריז באופן מלאכותי שפתרת אותה. אתה אומר, העתקות האלה יש להם הפוכה מקומית, העתקות שהן מופרדות שהן רק יותר הפוכה מקומית, יש להם הפוכה מקומית. באיזה מובן מקומית? במובן שהם זה הסביבה. אז אני חושב עליהם כעל שיכון פתוח של סביבה קטנה, למרות שממש לא שיכון, זה בריבוע זה לא שיכון, יש שתי פריביג'ים, אבל אני חושב על זה כעל כיסוי פתוח, בסדר? וזה כבר לא אותה קבוצה, אבל הם כן מעבוד קטגוריה, וזה מה שיאפשר לכתוב שיפים ולעשות טופולוגיה מוגבלת, אבל במידה רבה. אנחנו עוד 2 דקות צריכים להצליח.
הוא מסתדר, היה לו ויגול. היה לו ויגול.
וזה גם השתגעו?
אני יודע לפחות מישהו אחד שלא בא היום, בגלל זה, אבל אני לא יודע לגבי אחרים. קצת שלי כמה אחרים כבר יש.
כן, יש לך שבא, אנחנו שיש לך שם. אבל אני לא יודעת מה אני שתקע.
שיעור בכל זאת.
עכשיו 10, אז זה לא בעיה, לא אפשר לקום בשעה טובה. טוב, אני רוצה לשנות 5, כן?
זה עוד לא היה לי.
אני רואה שהיא טובה, אז בוא נסתכל לה. מתחת למסה קריטית של אנשים. אבל אם יש לך עוד שאלות, זה צריך לשאול. אני כבר לא זוכר, אתה אמרת לי פעם שעברה?
כן.
אז אתה יכול לשאול שאלות.
כן, זה פשוט ניסיתי על יותר מדי נכסות ב5 דקות.
כן, אפשר לעשות. למשל, הטופולוגיה של זריצקי לא אמר לך כלום?
ואני מניח שזה...
אבל לדעתי שזה זריצקי טופולוגיה on algebraic variety. Oh, what's the algebraic variety? Let's say finite algebraic variety. בדרך כלל החלטות שלנו פולינומי אלקוואפיינט. Some geometric object is described by polynomials. So you can define a closed subset just to be a subset which is a zero set of polynomials. Subline. And this is very weak property.
Every the algebraic variety is not for fixed polynomials.
Yeah, you fix a polynomial system of polynomial equations. 10 variables, 5 equations, 3.5. We'll get some something in n-dimensional space. Some geometric object, this is algebraic variable. Now, if you add more equations, you say, okay, also want x equal to 0, you get subset.
Yeah.
And this is a closed subset. So it makes sense it's closed because polynomials should continue. But if you don't have any topology on your field, then this is the only thing you can say. And these are the closed subsets. This is it. So the open sets are the complements. Like huge open sets. Or every open set is basically everything except for something that is not usual. So it is a topology, it satisfies the axiom of both, but it's not how to nothing that we use it for topology. It's still very powerful tool to describe kind of geometry, but because you also have polynomials, you have algebra, so you can use it to glue things together, but you can't use it to compute pi 1 or to actual stuff. Okay. So today I will try to frame depth, some level at least, and then we will go into model categories. So Vladimir already started on the categories, but I kind of realized that it's really rich subject. I kind of justify its own course, and in fact we don't have another course now. We don't know the material enough to do a full course on it, but probably we'll do 2 more lectures about it. We'll try to discuss it because interesting it's connected to a bunch of mathematics and beautiful. And so let us start. Oh, so last time I finished kind of in the middle of the notion of shifts. So we defined square shifts on a topological space X. I also had the notion of square shifts on a category, but for now it's kind of different, but related. And we have the notion of shift on X, which is square shift that is that satisfies this correlation axiom. I'm going to be good with axiom. Sorry, the shift axiom. But so first axiom is the separation axiom. It says that if 2 sections are locally the same, then they are actually the same. And the second axiom says that if we have a section in each of, we have some open cover and have a section in each open set, then we can and they agree on the intersections, then we can create one big section. So we formulate it. So now we talk about it on the level of sets, so we're talking about sheaf of sets, but you can basically do it for any category, and we formulate it like some diagram is an equalizer diagram, probably remember. But when you formulate in this way, you have like 2 parts. The restriction map monomorphism, and then that it's not onto, of course, but it is on epimorphic on the equalizers. So you always have a map between of you use the equalizer. When you are the cover to whatever it is here, like this sections, you always have a map like this, and separation means that it's monomorphism, and the second shift axiom means that it's actually an isomorphism or bijection if you're talking about. And now now we talked about shiftification. We talked about the other definition of shifts, the Lorentz shifts. So Lorentz shifts. X. You remember this topological definition, and nothing to do with open set, just one map and this. And we had a functor from here to here. And I don't remember, did we define the functor to the other direction? Yeah, so for any sheaf, we constructed a topological set, considering the stops of the sheaf near each point, we lose them all together, and where a functor random direction, and I think I gave an exercise that is stated that these two functors are inputs. But now you can find this funny thing. You also have a functor. Sorry. You also have a functor like this. Just defined in exactly the same way. So if you have a per shift, you still can define stops. You still can consider limit of u, u, limit of co-limit limit. What? Separated per shift. So only the first shift axiom. You have shift of the map is monomorphic. Any section is determined by its restrictions to the open subset of the path. So you have a functor like this. And now you can compose this functor with this functor. And then you get a nice functor like this. So you have a functor starting with a per shift and making a shift out. And this functor is called the shiftification of the per shift. And so this is one way to define it, but it's a bit technical. Yeah, I don't know. But you of course can define it generally by using just not actually constructing it, just factorizing it. You ever forget to functor from shifts to per shifts. And because any shift is also a per shift. And this forget to functor is a join. For it is never quite a join. And we can check what direction makes sense. So in fact, what does this functor, the shiftification is a join from one side to progression. You remember? What?
Left adjoint.
Left adjoint.
And this will be
Completely trust you. And so you can define the shiftification just to be the left adjoint the forget the functor. And this is just one of the constructions. Now this construction is nice and beautiful, but somehow it uses things that not really related to the story. This stocks, this how do you call it? This level shifts, level definition of shifts. So somehow one could expect that there will be more like direct construction that related to the open count. And how you would do such construction. So what we want from the shift axiom? You have f of u maps to product of ui. And here you have two maps, product of f of ui, uij, when uij is defined to be ui section. And you want it to be equal, yeah. So as usual, when you try to do a joint functor, what you do when you do a joint functor? You take an object and you just try to enforce it to be something that it is not. In this case, you take a per shift, try to make it to be a shift. So you want this to be an equalizer diagram. So you want f of u to be equal to the equalizer. So you can just redefine f of u. So let's define f theta of u to be equal to the equalizer of this thing. Let's call this thing some name. Diagram. Okay, so first of all, you want to demand that your category will have equalizer. No problem. Let's talk about the shifts of sets or shifts of abelian groups or equalizers. And then the second thing that you probably immediately see here is that it's not really a well-defined procedure because we want it for any cover. So let's start with choosing one cover. So this will depend on the cover, and this will depend on the cover. So C with the cover with C. the cover X and UI just gives line. So you have one global cover of the entire X, so it gives you a cover for each open set. And with respect to this cover, you constructed a new for a shift, which is more likely to be a shift than the previous. Because, okay, at least it seems that it wants to satisfy the shift axiom, at least for this cover. Yeah, in fact, it doesn't satisfy the shift axiom for this cover because UI and UIJ, you don't really change the definition here because it's just the same, like just covered by one piece. Okay, but of course, this should not be the correct answer because it depends on the cover. But now what you can do, you can take the limit over all cover. Yes. Yes. Shifts about open cover. When we say in topology that something happens locally, it means that there exists an open cover such that something happens.
Why do you take a disjoint union?
Did they take or no? This was mistake. And XI. XI also.
Yes.
So. So there is a notion of refinement of cover. So a cover is a refinement of another cover if for any. So we have cover C1 and C2. So C2 is a refinement of C1 if for any X and any U Z. Not so that includes X, but it's an element of the cover C1. There exists U V, and which also includes X, and it's included in U, and element of cover C2. So the open sets from C2 are smaller. For some of them might be big, but they are better than enough open sets to cover all the sets in C1. So you can see that if we have a refinement of the cover, then we have a map for one direction from where to where. So in this case, be the C2 of U, and be the one of U. I think the map is like this. Am I right? No, no. They're wrong. Because any yeah, no. Any you have restrictions, so you have the cover in one, you have a coherent collection of sections that are in the equalizers. You want those sections, you can restrict them to the section. Can you restrict them to a section of C2? Not really. C2 might have a larger set, so you don't want this definition of refinement. I think you just want that any open set in C2 will be a subset of an open set in C. And then you can restrict there. Yes, yes. Okay, so it's not the standard definition of refinement, but it's here. I need to use it. Any EU E2. They're both covered, so the cover all the points. And this is the E1 such that you. And then you can, if you have section for each of the open sets in C1, you can, and now you have an open set in U, you can choose as open set of C1 that includes set. And then restrict your section. And of course, you can ask what would happen if I choose differently. But since you start with element in the equalizer. So a section that is same is that when you restrict to the intersection, you get the same section. So it doesn't really matter how you or what you choose. So you have such a map. So when your cover become thinner and thinner, you get maps to this like partial simplification, and then overall you can take the limit, and this time there. So here C2 is more a final cover, so you have to take directly. Also in the stock, you take directly, not an interesting. Yes. I see some point. Yes, yes. The limit. So which is in co-limit, yes. Co-limit. And FC of U when you range over all covers. And all covers are poset with respect to this. And now this guy has a very nice, very good chance to actually be a sheaf. So this kind of a good candidate for the sheafification, or sometimes F plus. The best news is that in general it's not a sheaf. It's still a sheaf. So it's kind of weird. You did this thing, you expect it to be a sheaf, but of course formally it's not obvious that it is a sheaf. Because you change this guy and you change this guy. So yes, this becomes the equalizer, but also it took a limit, but okay, it's still some equalizer. But you change each of these guys. And you try to prove it is sheaf, and you see that you cannot do it in sheaf. And there are counterexamples. I think just there's probably just 10 bad topological spaces, but maybe even not so bad topological spaces, but bad sheaves on them. If they're weird enough, you can. I don't know the counterexamples, but everybody telling me that they are, so I will try maybe to for the next time to prepare for counterexample. And so this kind of doesn't work. But in fact, you can make it work for others. And the thing is that when you do it, and you maybe don't get a per sheaf, but you do a sheaf, but you do get a separated per sheaf. And if you start with separated sheaf and you do it, you do get a sheaf. So what is the solution? Just doing it twice. And it's a look weird, but yeah, you're just doing it twice, and the sheafification. And one way to think about it is that the F plus construction is not a adjoint functor to the forgetful functor for per sheaves to sheaf, but it is an adjoint functor for the functor from separated per sheaves to per sheaves, and from sheaves to separated per sheaves. So you decompose your functors into two pieces, and then you find the joint to each of them and compose. Very standard way to compute adjoint functors. Okay. So this is a sheafification. But usually one time is enough. So for many cases, one time is enough. So let's do example of sheafification. So probably the most basic example is the constant sheaf. You have some topological x and some set x, s. So you can define the constant per sheaf with value s, f of u is equal to s. That's for any open set and give s. Oh, now think about it. Maybe this is a good counterexample because for any open set, including the empty set, I want to give S. So let's see, is it a separated per sheaf? Probably not because of the empty set. If you have a set U, which is equal to U union is an empty set, is it true that any section in U
union or disjoint union?
It is joint, but also union. It is a cover. So any section in U, you can restrict it to U union to U and restrict to the empty set. No, this will be 1-1. So I'm wrong. So this is separated by sheaf. So I claim that its sheafification is the constant sheaf. So do you remember what is the constant sheaf? The sheaf whose sections are locally constant functions from U to S. So let's see what we can do it. So yeah, so the reconstruction is very simple here. The stocks of the constant by sheaves are the set S, and just the topology will be just product topology, and then you take section of S times X, so S is a discrete topology to X, and sections of CC, so exactly locally constant functions to it. And let's try to do this other simplification. So what's the idea? We have open cover, and what is F in the C of X? So these are functions which are constant on each open set from the cover. So they're not locally constant. No, they are locally constant, but it's not all the locally constant functions. They have to be constant on each open set from the cover. And now when you take the limit over all covers, so you get functions which are constant on some with respect to some cover. This is exactly locally constant function, because if you have locally constant function for any point of a neighborhood where it is constant, you get a cover, or where it is locally constant. Yes. So this is the simplification. Now the second example is kind of typical because when you want to, there are lots of constructions that you want to do with sheaves. So we have some construction. So let's talk about sheaves of abelian groups or sets, never mind. So you have some construction for sets, for abelian groups. Then you want to say, let's repeat this construction to sheaves. And the most naive way to do it is say, okay, let's just do it for each open set separately and just repeat the construction. And then we get something. We get per sheaf. Usually we get per sheaf because if the construction was functorial, we still have restriction. But often this something will not be a sheaf. Then you have to specification. And the best example is image. We also two sheaves F and G. And you have a metric with them. And then you want to define the image of this map. And image is a categorical construction, so you want to prove the existence of the. And in the category of sheaves, both sheaf with various in sets or sheaf with various in abelian groups, there is a well-defined notion of image. So the image exists. But the naive way to define it does not work. For kernels, the naive way will work. So if it's sheaves of abelian groups, you can define the kernel in a very naive way. For any open set, you define the kernel, you get per sheaf of abelian group, and it's very easy to see that it is a sheaf. But image, if you just walk like this, you will not get a sheaf. I will try to make an example. But you will get a per sheaf which is not a sheaf. So the image of a map between two sheaves is a sheafification of the image as a map of per sheaves. So in the category of per sheaves, you have image which is very simple, just a naive image. In the category of sheaf, you also have image, but it's not a naive. So let's see whether I have a nice example. We have. If we can start with in order to see the fact that the image is not the same as a naive image is related to the fact that the topology is not trivial. If something is constructible, then it's also not true, but you expect that the image will behave like the image, the naive image. And so let's start with a circle and take what we want to take. Okay, maybe we'll do that for the break. So this sounds really good. No. Okay, so this is a very typical example of how we use stratification. And we define if you want to construct something, just construct it naively and then stratified. And the corollary from this is this lemma, x is whatever. Huh? The category of ifs of abelian group S the shifts of abelian groups over a topological space X is abelian. And more generally, shifts with value in any abelian category is an abelian. And this is correct theorem, correct lemma, but it proves it's not naive. So Brush shifts with values in abelian category obviously abelian, and shifts with values in abelian category is also abelian, but it's not obvious because the kernel is defined in the same way, but the co-kernel you have to shift. And whether it means that the proof is not obvious, it means that the functor, the forgetful functor will shift into abelian groups of things to do Brush shifts. Abelian group whatever is not an exact functor. Because exact functor, I don't remember whether we defined it, exact functor is a functor that maps an exact sequence to an exact sequence. Equivalently, it's a functor that maps, it also has to be additive. That's what this is called additive. And equivalently, it maps short exact sequence to short exact sequence. And I think that assuming that it's additive, no, this is probably not true, but at least it implies that it's commute with kernels and co-kernels. And it's mostly equivalent. I'm not sure it's equivalent, but it's mostly equivalent. So if it's this functor commutes with kernels, but it does commute with co-kernels. So it's not.
So this is a complication.
There's this complication that I talked about that you have to simplification. That but when you take the naive co-kernel, it's not the actual co-kernel because it's not a shift, you have to shift. And so here, here the co-kernel here will be shiftification of the naive co-kernel, and the co-kernel here will be just the naive co-kernel. Okay. So I think this is enough about shifts. Do you have any questions about shifts?
How is this true?
What?
How is this true?
Is that this is abelian or that this is not abelian?
That this is a
And so the construction, you have to prove that kernels exist, co-kernels exist, and the image is the same as the code image. Yes. So the kernel, you just take the open the kernel. The co-kernel is a shiftification of the co-kernel. Now you have to prove that it's a co-kernel. This is rather simple. So you use like the fact that the shiftification is a joint functor from pair shifts to shift, and the fact that in pair shifts, the naive co-kernel works. Okay, we'll do some diagram checking on it. And the last axiom, you use the fact that the value category can be
which can be.
the values category. So in our case, shifts of abelian groups, but it works for shifts with values in any abelian category. So yeah, if you have morphism between two shifts, which induces isomorphism of the layer of stocks, then it is an isomorphism. So you use this. Okay. So another depth that I had is about push out of group points. So I will try to do it in two ways. So one like general way how to construct and push out of group points, like not to compute it, just to prove that it exists. So maybe it's something big or something not explicit, but it's okay. And for this, I need this technical tool of adding a morphism to a group point. So suppose I have group point gamma, and I have some pair xy, pair of objects in gamma, and let's assume that they're different. It's not really important. It might be more just. And now I want to describe the group point generated by gamma and by this single additional error, which is maybe there are some errors between x and y, but I ignore it. I just want to add this error. And so this you do in the, so let's call it tilde. So objects of gamma tilde and just objects of gamma. And then you do basically the only thing you can do, what are morphism in gamma tilde from x to y. No, not this x, I'm sorry. A and B. So the collection of errors of morphisms of words like this, alpha, or let's call this by some symbol epsilon. Epsilon plus minus 1, beta, m alpha 2, epsilon plus minus 1, etc. You have to end it at some point, but now you can choose whether you can enforce that you always end it with some alpha n. Just it can be identity if you want.
But they're alpha.
So alpha i's are morphisms. Gamma. And this thing should make sense. So all the morphisms here have to be composed.
So epsilon is actually a morphism.
Epsilon in the new category is a morphism, so I consider it as a morphism, but not in gamma tilde, but its source is x and the target is y. So alpha 1 has to be from A to Y. Or from A to X. So from A to X, or if you put here -1 from A to Y. Yes? And alpha 2 have to start with X and finish wherever and finish either in X or in Y because you have here an X. That's it. So the version makes sense. But okay. The morphisms are controlled. And you need some equivalence relation, but the equivalence relation is very simple in this case. So basically, the only thing that you allow to erase is if you have an identity here, and here you have plus and -1, then you can erase them and like it's simple and leave this as. So you don't allow to go. You can do it like equivalence relation, or you can just say that you are not allowing identity here if you're going back and forth. So you're not allowed to go back and forth without doing anything. You have to do something. So now if you have several morphisms that you want to add, you can just do it one by one. So now how you define push out? How you construct push out? X, Y, Z, So first of all, you just consider the category X, Y, Z. And then you add the point X, Y, Z, that's union Y. Z. And then you add the morphisms, add the pairs with Z, comma, F of Z, and Z, comma.
For all Z.
Forward. So how do you say in English? יצאתי לחובה?
I completed my.
But yeah, but on the minimum, yes. I kind of fulfill the promise, so I define you the push out. But still, you can ask, okay, what happened on the factual end if I have here? So we know all the groupoids are union of BGs. So here union of BGs, here union of BGs, other BGs of course, and here union of BGs. And you have maps. What do you get? And here it's kind of so you can do this thing and say, okay, this is what you get. So I can define you the groupoid, but you want to know, okay, the answer is also union of BG, so we want to know generators from the automorphism group of a single object, say in X or in Y. In Z you don't really need because Z doesn't really add new objects. Each object in Z is isomorphic to some with its image in X and with its image in Y, so you don't really care. And here, so of course you can say, compute what happens. You can add more and more. More morphisms and ignore what's not a morphism. So now the automorphisms are morphisms start and end in the same thing. But here it will not be easy to disguise them by generators and relations. Just we have a very long list of morphisms. So let me try to do it slightly differently, and then I go back. I will try to go back to equation 2. So you remember the Van Kampen theorem. And Van Kampen theorem says basically that if we have a push out of topological spaces, then the fundamental groupoid is a push out of the groupoids. So the thing is that we can use it the other way around. And it looks stupid because we want to compute the push out and the fundamental group of the push out. And now I'm asking, I'm using that other way around, but it makes sense. Because if you have a very complicated topological space X, and this have a fundamental groupoid, then you can construct much simpler space, say X prime, which will have the same fundamental groupoid. How you do it? You take this fundamental groupoid, you can write it as union of BGs if you want, and then you can take a point for each object and add an arrow for each element in G, the automorphic group, and at the surface, each time you have G1 times G2 equal to G3. Or more generally, you can write as this G with generators and relations and add an arrow and out a loop for each generator and surface for each relation. So just the most standard way or most canonical way to write a group with generators and relations is say that all the elements are generators and these are the relations. So this is the topological space, and it's kind of two-dimensional topological space. If you know what are CW complexes, it's a two-dimensional CW complex, and it has the same fundamental group as X1. So now, when you start with two groupoids, how we called them before? היה כאן ממש חד קלע. X, Y. So each of these groupoids you can replace by this two-dimensional CW complex, like two-dimensional topological space, and then you have to compute the push out in the category of the topological space. And this is rather easy. So how you compute the push out to the bigger topological spaces? So the idea is that you take each point. So you take like z times the interval I, and you glue it. So you first of all you start with the three spaces x, y, and z, and then you glue z times I to z and to y. So z times you glue to z, and z times y 1 you glue to y using the method you have in z. And the same you do with x, and this for two.
Sorry, how did we reduce push outs and group points to push?
Because each group point you can construct a topological space. Okay, let me write it. So corresponding topological space, let's call it. No, B is basically I don't know. Let's call it realization of x, realization of z, and realization of y.
So each point is a fundamental stop.
Yes. And I can do it in a canonical way, just to the object of the groupoid I assign points, and to the morphism of the groupoid, let's say the all automorphism, don't have to do it, or if we can assume it, I assign loop, or if the automorphism pass, and if the automorphism in this path is going to be a loop, and each time I have a composition of two maps which is equal to a third map, I add a disk that connects this pass, not connect with this pass and this pass. So maybe I should write it like G1, G2, G3 here. So this is a loop always, even if G1 and G2 are not, they have to be composable. Even if they're not loops, this is always a loop. And then we have a disk that closes. So it's two-dimensional. And then I consider this. So the problem is that now I'm getting something three-dimensional. And because this was two-dimensional, this was two-dimensional, this two-dimensional, but z times I is three-dimensional. But I still can compute its fundamental group. And although it is three-dimensional, I can just ignore all the self-dimensional thing. So basically what I can do, because they just don't affect the fundamental group. So basically what I can do, I will do vague, but I can take Z and forget about all the two-dimensional cells in Z, because they contribute three-dimensional cells in the push out. So what it means? It means that in Z there were some groups. I just replace these groups by free groups. There are no I change the fundamental properties of Z or RZ. It will not be Z anymore, but it will not change the answer. So this is a proof that it doesn't change the answer, because you know that from topology of algebraic topology, people propose, and then that this three-dimensional cells does not change the fundamental. So it means that if you have push out of such groupoid, if you replace that with groupoid with the same with the same objects, but let's say that each isomorphism class in Z is just one object, so say the same object, but the automorphism groups are just three groups on the same all elements in G without any relation. We just consider it as a set. And this new like Z tilde will have the same push. Z tilde is much larger groupoid than Z. You have map from Z to Z tilde, which is essentially subjective onto the level of objects, and it's also onto the level of morphism, but it's very not one-to-one of the level of morphisms. And still this push out and this push out are going to be the same. And then you get a two-dimensional, and after the break, I'm going to describe it, two-dimensional CW complex, so a graph with surfaces and cover and some of the things. And its fundamental group is its fundamental groupoid, so is a push out of this diagonal. Oh, this diagonal. So let's make
לפעמים מצחיק. לפעמים. אז שעומד על המקום שלי. כאילו,
איפה אתה מגיע?
כן, זהו, כי בערך 2 דקות לפני, כאילו זה יותר רק אני ורן, טוב, כל השאר הרבה דקות בעיבוב. כן, אז לא, אני לא רוסי, אני לא אזור.
בסדר, יש הרבה אנשים בכלל לא עושים.
כן, אבל בטח. כן, אבל יש לימודים אחר. זה לא... כן, זה לא... זה...
אין איפה הידיעה שלי.
לא, הוא כן, הוא אמר לי שהוא... כן, חוגג. יש מספיק...
רמי, לי אישית החלק האחרון שאמרת לא היה בו.
על מרחב הדקות.
כן.
עכשיו שנזכרתי שאני צריך גם לספר לך על הדוגמה על השיפים, אז אני אנסה לעשות את זה. out. Okay, so let me try to draw this picture in any way to become more clear and computable. So um, so we have X. We want to compute automorphism of an object in X. The one thing you can see is that objects which are not isomorphic to this object will not be relevant for us. So we can assume that in X there is only one object in X which are not isomorphic. This object, or in general, objects which are not isomorphic. So this object will not be relevant. So we can assume that in X we have one object, but several different objects in Z can be mapped to the same object in X. And the images also can be, sometimes they may be the same, but there's several different objects in there. So we can assume this situation. So all the objects, there is only three. There is only one object in X, and in each item of freedom class in X, Y, and Z, there is only one object. And we have this picture. So now we want to understand an automorphism groups of this kind. Oh, okay, so first of all, we want to construct a topological space. So what we do, so here we have a topological space. So here we have group of automorphisms G. Here we have groups of automorphisms HI. And here we have groups of automorphism. So HI, we don't really care about the group, only about the generators. Or Z. So we can do generators, but we only care about the elements of HI. We don't care about the group structure. Here and here we do care. So here we consider, let's call it the realization of G. Sometimes it's also called BG, but in this course, BG is a groupoid corresponds to G, which is just a groupoid that we have here. And let's call it the realization of G is a topological space, which constructed in this way, we have a point. For each element in G, we have a loop, and each time we have such an equality where the disk whose boundaries are these three loops. So this is a realization of G. And here we have let's say it's a stupid realization of HI. So just point and loops without surfaces. No, sorry, no, HI we don't need to. And here we have realization of I. Several of I, so each of them has its own realization, just put the disjoint union. But now we add passes and add surfaces. So what passes we have for each I? We add this path. So each object for each I, so I for one. C. So the number of isomorphism classes in the groupoid Z. So for each I like this, where the path from here to MI. So one of these passes, we think about it as if it passes through some object, but we don't have to think about it this way. This M1. Boom. Oh. For each I, we have how we call this map? From G to I, GS. So G I point from this point to G of I. There are I element here, so G of I will have pass. So sometimes we'll have two passes with the same head, and sometimes the passes with different I's can be passes with distinct head. And we have a surface. So each time we have HI, HI, we add the surface. Just how do we do it? We have, let's call this point E, and this point G of I. So remember you have this pass, and you remember that you have a loop from GI to itself, which is G of HI, and you have a loop here from HI to itself, which is F of HI inverse. And now we want to add a surface. Close this in. Because automorphism, okay, I don't need to, I will explain because of that. Yes, so this is our new topological space. It's the topological space that we have here, with passes and surfaces, many topological spaces that we have here, and lots of like cylinders or lots of strings that connect these topological spaces, and some cylinders between them. And the claim is that pi1 of this topological space is also the fundamental groupoid, or if we like this connected topological space, because it's connected to this point, so the pi1 of this topological space is push out the automorphism group in the push. Is the construction clear? Or should I repeat? Clear? Clear? What's this? Look at it and also. Sure. Okay. Why is this construction corresponds to push out of topological spaces? And what topological spaces? So we have R of G. So we have a pseudo point. X, Y, and Z. So we have R of X, R of Y, and let's go R zeros. So R of X is exactly what we say here. It's just one point and surfaces. R of Y, very similar, several points, and each time we have loops and surfaces. What is R0 of Z? It's just like, or maybe it's better to call it R1. One-dimensional skeleton. So it's just a graph. The vertices are the object of Z, and edges are the morphism from G. And this is it without any surfaces, so without the group structure. Now we can take here R2, adding the surfaces, but these surfaces will contribute only for three-dimensional pieces in the push-out, and so we don't care about them. And so we take only the loops. And now we say that we add this for each, like the cylinder R1 Z times I, we add it twice, yes? And glue them along R1 Z. So adding it twice is the same like adding it once and just glue one side to here and the other side to here, because it's immediately just smoothing it up. And when you add it, what is R1 of Z times I? So each time you have a vertex in R1 of Z, you get a string, a path that connects a point here to a point here. And each time you have a loop in R1 of Z, you have the cylinder, which is exactly a cylinder that we got. So this is a way to compute the push out of groupoids, but you can complain that this way it's too topological, yes, it's constructed on topological space. So now we can recall how to compute fundamental groupoid or fundamental group of a topological space, which is a CW complex. So we have two-dimensional CW complex. So we have passes and we have surfaces. And there are two ways to do it. One way is basically say you take as a free, not the free, you take a group generated by all loops that are along the passes, but then you have to add lots of relations each time. It's not that simple to understand what are the relations. So basically the idea is that if you have two loops which have a common part and you compose them, like at some part you go back and forth, so you can arrange with back and forth out and you get the same thing. This one kind of relation. And another kind of relation, these are the surfaces of each time. You have a loop and you have surface, and your loop will go into like this. So you can replace one side of the surface with the other side of the surface. And then you can use all of this to write relations. And what we'll have in this case, so what kind of loops we have starting in this point and ends this point. So we have the elements of G. And we have loops that goes like this, tap, 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 tap. Here you can do something and then go back. Now you don't have to go back to the same path, but you can go back in the same path. You can go like this, but then you have to do something non-trivial here, otherwise the loop will be trivial. And then you go back. And basically this is it, these are the all generators. And what are the relations? So two types of relations. One type of relation is when you did such a loop, and then the next loop, the beginning of the next loop is like the end of the previous loop. And then you can cancel them out, and maybe here you have some automorphism, but then you can compose those two automorphism to one. So this is one kind of relation. And another kind of relation, more complicated one maybe, this is coming from elements in this HI, and these are exactly the relation like this. So you can go from here to here, and then do HI, and then go back. It's the same, like first do here, like the same HI, if this HI is something that came from here. So you can do it first here, and then, because of this thing, you can go like this, or like this, and then like this, and this will be this. So you can write it with generators and relations of this type. And yes, probably this is the best way to describe it. It's a bit long, but it's it. So generators are easy. Elements of G and going like this, doing something here and going back. We're using this MI. Relations are more tricky. The naive one when you go back and forth, and the tricky one that coming from H that you can do it before you go or do it after you go. Each time you have an object here that maps to an object here and do it here. So you can do it automorphism. It's automorphism here, here, and here are the same. So here we didn't discuss them at all. They're not like part of our generator. So here and here you can take in the back and forth, like you do in an amalgamation problem. And there is another way to describe pi1 of a space, which is kind of shorter, but it depends on choices. So if you have some CW complex, so you have points, you have some passes, there's passes, no, this, and you have surfaces, you want to compute it by one. So a nice way to do it, or some way to do it, is you choose a spanning tree of the one skeleton. So the one skeleton is just points and the passes. This is the graph. Any graph has a spanning tree. This you know, yes? And you can choose a spanning tree, and then you basically contract this spanning tree to one point. And now you have only one point. And then your generators are the loops and your relations are the set. So here you can also try to choose a spanning tree. And it will be not that simple, yes, because this passes like this, but each time you will have to like each time you have two elements in Z and both the same element in Y, you have to choose one of them because otherwise it will not be two. And then you can contract everything to one point, and then you will get less passes. So basically, the passes. So all the passes that are going to the chosen points are considered as trivial. You contract them, and then only you allow to get passes which are not from the chosen point. So all those passes dies. But of course, you add all the groups of I to here, and still you have some of the passes that are like giving you new loops and new relations. So okay, this procedure I didn't see it so through, and probably would become it's shorter, like less relations and less generators, but it's less clear, like it's harder to write down. So probably it's not that. So it's more compact, but usually less. Okay. So before we go into Monoid, I just recalled that I wanted to give some, or maybe I gave already, some other examples of sheaves, which are we talked about the constant sheaf, and then we talked about local constant sheaves. Can say what is a local constant sheaf. A local constant sheaf is a sheaf that locally isomorphic to the constant sheaf. So if there is a cover such as for each open set, you have a constant sheaf. Your sheaf is isomorphic to the constant sheaf. So the constant sheaves, the sections of the constant sheaves are locally constant functions, but it is still the constant sheaf. The sections of locally constant sheaves are not locally constant functions, are something else. And what's this something else? So on the level of Leray definition of the sheaf. So you remember that where the Leray definition, X belongs to F. And extending in general can be very ugly space, but the special case of Leray sheaf is just a covering. And then the corresponding Gaussian sheaf will be just sections of this covering. And this is exactly the case of local constant sheaves. And why? Because constant sheaf is just the Leray organization is this. So this is constant sheaf, and something that locally looks like this is exactly that. And this is a nice collection of sheaves, and then there is a notion of constructible sheaves, which basically sheaves that you can construct for locally constant sheaves using some simple alignment operations. But then there are completely different examples of nice sheaves. For example, the sheaf of continuous functions of X. For each open set, you give the continuous collection of continuous functions. And if X is a smooth manifold, then you can consider the sheaf of continuous smooth functions. And if X is an algebraic variety, then you can consider the sheaf of regular functions. Then, if X is complex analytic variety, then you can consider the sheaf of complex analytic functions. There are many examples like this. And these examples, okay, by the correspondences between Gaussian and Leray sheaves, all can be realized as a sheaf, but this will be a complete disaster. Yes, if you try to understand what are the stocks here, the stocks of continuous functions, it's something rather complicated. Yes, it's continuous functions up to equivalence relations that two functions are equivalent if they're equal on some small neighborhood of X. And then you take the discrete topology on this huge collection, but the total topology will not be discrete at all. So it will be very, very non-hard. Each fiber will be discrete. In the instructions is what you have. Each fiber has to be discrete, but they're all there are no two open neighborhood, no 2 points in the fiber are separated by like the house of axiom. So any two open neighborhoods will intersect. Because if you have two stocks of continuous functions, so continuous functions that we define only in a small neighborhood. So for any larger neighborhood, or for any neighborhood, you can find two functions that will be the same outside very small neighborhood and will be your two functions inside even smaller one. So very, very non-hard stuff. Situation, all the others are also basis. Maybe this one a little bit better because it has uniqueness theory, but not much better. And these shifts are very useful in order to define topology. So say you want to define geometry. Say you want to define what is movement. So one way to do it is with atlases and charts, etc. Another way to do it, you just say it's a topological space X together with a shift that we will call C infinity of X, such that locally each point of X has a neighborhood, and such that this pair of the space X and this shift will be isomorphic to the pair of Rn or open set in Rn and the shift of smooth functions. So if you want it to actually work, you need to put some more conditions. So one thing that you usually want to do is not to talk about abstract shift, but about shift of functions. So shift together with embedding into this shift, or more generally just a shift of all functions. And
so infinity of X. So locally
no, it's not locally constant at all. It's very any point it will not be. There is no neighborhood where smooth functions become locally constant functions.
No.
But it is a shift. To be smooth function is something that is determined on the local level. You have a function, you don't know whether it's smooth or not, you can check it locally. There is this notion of shift of function. Shift of function is a shift which is subshift of this shift. Now you know what is a shift, so you can define it this way, but it's in fact a simpler notion than the notion of a shift. Because you just can say it's a collection of functions for any open set of collection of functions, such that in order to the shift axioms become much simpler and much more concrete. So in order to be in this collection, it's sufficient, necessary and sufficient that for any point and there exists an open neighborhood such that you are inside this collection. But the being in this collection is something that you can check locally. So and this is the way to describe geometry. So you can say that smooth manifold is a topological space with a shift of function that locally look like C infinity. And sometimes you add some additional axiom. So it's Hausdorff and power compact. And this is less common here, although you can do it here, the C infinity work. In the algebraic code, it's kind of the main way. So if you want to define algebraic variety, so one standard definition is the topological space with a shift of functions that locally look like an affine algebraic function. With the theoretical topology and the shift of a regular function. And in fact, if you can at some point forget about the fact that you want to talk about shift of functions and just consider abstract shift of, say, of algebras, and then you get then this is more adapted to notions like schemes, where the regular functions are not necessarily actual functions. So this is one very nice application of the theory of shifts, that it allows you to describe new geometries. Not any geometry can be described in such a way, and not always this is the best way to do it, but this is a good way. Okay, so let's go to monoids. Any questions before monoids? Not monoids. Okay. So we'll all remember what our monoid are.
In the very beginning of the course, you wanted to give an example when we consider not the sphere, but the parts of the sphere. Sphere, and dimensional sphere. And you said that it's don't have such a group of symmetries, but it carries something
I think I said already in the beginning. So you can consider the category of metric spaces. This is a perfect category, and basically any question that you can ask about metric spaces or maybe Riemannian manifolds, you can rephrase in this category. So maybe not every question, but many questions. Unlike the category of auto isometries of some curved sphere, which so this is a group, but this group gives you zero knowledge about this this topological space because it's a trivial. And the category is very non-trivial, and I don't sure. So probably there are some questions that you need to know already. So there is, for example, the forgetful functor to measurable spaces. So this is something that maybe cannot be described in terms of the category. But at least to ask whether two metric spaces are isomorphic, something that you of course can ask in terms of the category, and many other things you can also ask in terms of a collection of the embedding of a given sphere to R3 is something that makes sense in terms of the category. So it's much richer than just automorphism.
Okay. Another question is this. There is an opinion that geometry should be defined as a space and the group of symmetries which acts on this space, which is more restrictive than
Yes.
set, but
And not every geometry can be defined in such a way, but more or less any geometry can be modeled by something.
yeah, but is category theory useful? This approach.
So
Group of
theory generalizes this approach. So every so group is a category. That's all. A BG is a category.
Yes.
And so this is a special case. So any geometry that you want to describe a group of automorphism, you can do it such as a category with one object. But some geometries cannot be described with group of automorphisms because, for example, because the group is trivial or not non-trivial enough. But category of geometries of certain type is usually enough for
Sure, but can you give an example?
I just said an example, metric space. You can study the category for, say, Riemannian manifolds. You can study the category for Riemannian manifolds, and I don't know what theorems in Riemannian geometries you're interested in, but most of them you can reformulate in most of the language of the category of Riemannian. Eclectic manifold. So, like usually, when you say you study Riemannian manifold, it's more or less equivalent to saying you study the category of Riemannian manifold. So almost from difference. When you say you study symplectic geometry, you study the category of symplectic part.
Oh, but it's not a group approach.
It's not a group. This is what I say. Now, when you say you study Euclidean geometry, you can say the same as study the automorphism of say Euclidean. This is called, and this is also a category with one object and automorphism. This is correct, but this works for Euclidean geometry. It doesn't work for hyperbolic geometry or spherical geometry. It doesn't work for general Riemannian geometry. It's not say you study Riemannian geometry. It's not the same as say you study the group of automorphism of Riemannian or all of the two. But many of them just have no automorphism, but they are very distant. But they all represent different functors from the category of Riemannian manifolds to.
Can we say some nice categorical way? What it is to study spaces which locally looks like something like Euclidean space or Pollock space?
Not really. So okay, there are several ways. So first, the usual way to do it is you do it for topological spaces, yes, and then now if you have, you can ask if you have some category C, say Euclidean spaces, but Euclidean spaces say with C infinity metric spaces. Well, no, we can also talk about Euclidean spaces with Euclidean geometries. And you want to define category C tilde whose objects will locally look like objects. But don't have functor from C topological spaces, so I cannot just say take topological spaces such that nobody like C, object C. And so there are some ways to do it, and maybe we'll talk about later when we talk about science.
So they're not related with just shifts of functions. Something more complicated.
It's related, but it's not that simple. Yes. So yeah, the idea is that you can consider pressure on C, and C is embedded in pressure C by another. And then you can try to find C tilde here. So you can try to say that some shifts are better than that. For example, because there are shifts, they didn't define notion of shift category, there is no such notion, you need to give some additional structure on C. Just make sense of this notion, but yeah, sometimes you can. One of the ways to define algebraic varieties are defined like pressure shifts on the category of a finite algebraic variety. Yeah, and theoretically, you can do it also for smooth manifolds, etc. So smooth manifolds are also pressure shifts on the category of Rn. The category with one object Rn and smooth maps between Rn to Rn, factor of noise. And then there is some way to define the category of algebraic variety inside the category of pressure shifts in this category. Sorry, smooth manifold. You have a functor from smooth manifold to pressure shifts there. This function is a functor is full faithful, like in the element it works. But to define its image, so of course you can say, okay, let's consider the image, and this will be our new definition of smooth variety. But this new definition is based on the old one. You can try to do it from scratch, and theoretically it's possible. Maybe this is next chapter if we have time. Okay, so we talked about monoidal categories. So you know what this means. A is a monoidal category, and I understood that Shachar also talked with you about duality. Okay, so let me shortly recall duality. It's a little bit complicated topic. So we have several possible definitions of duality. So I think the definition that I like the most is that if we have an object X, then we have a functor. I don't know how to call it, Ex or a, which is Y maps to tensor. And then we can ask politely this functor to have an adjoint. Of course, I don't remember do what left adjoint or right adjoint. And we can ask very politely this adjoint to be also functor of the same type. So we can say that X and X star are dual if P and P star are adjoint from certain direction. And then surprisingly, maybe we'll call it Rx. X star. If Rx and R star are adjoint for one direction, then you will also have L. No, this is L. L because X here is on the left. So we also have Rx and Rx star, which is product from the right. And they also happens to be adjoint, but for the other direction. So we have two equivalent definitions of when X is dual to X star. One of them that these two functors are adjoint, and the other that these functors are adjoint. And the reason that these two definitions are equivalent is because you have the third definition that probably Shachar gave you, and which is equivalent to both of them. And the third definition is that you have evaluation map like this, and co-evaluation map like this, and some zigzag identity. The probably Shachar and he gave you in the exercise session. And I will talk about it in a moment, or in several moments. But I just want to explain what is the relation between this definition and this definition. So you know that tensor product is associative. So once you have a map like this, what does it mean? It means that if you have Lx composed with L star composed with Lx, I'm doing it correctly, I hope yes. Obviously in this direction, you have a functor to the morphism to the identity functor. Yes, because identity functions that product with 1. And tensor product is associative, so you can take x tensor product with y, and then tensor product with x, and using this isomorphism, this morphism, you get a morphism. And the opposite thing give you like this, Lx. And now we didn't do it before when we discussed adjoint functors, but we should have do it. So each time you have two adjoint functors f and g, then you have a map like this. And you also have a map of this. So I don't remember who have to be adjoint from what type, but once you have one junction, you have both of these two maps. If you have the other junction, then you
One
have
of
to
them
have.
must be the opposite.
And what we did get away. And now you can ask the other way around. Suppose you have two maps like this. Does it mean that f and g are adjoint? And the answer is general no. If you want to make it yes, then you need some commutative, some diagram to commute, so some quality of some positions, which is exactly the same, I don't know, zigzag or I don't know how we call it, identity set that you had here of relating these points. So what does it mean? It means that this definition is equivalent to this first definition. But for the same reason, it's also equivalent to the second definition, because you can read it the other way around. You can take this product from the right, but then the composition will be the other way around, so you will get a different adjunction. So this definition is equivalent to both definitions, and then you see these two things. Which is nice, so you can, so this left and right have two different meanings. So you can change with left and right by changing the order of the product in your category, but you also, they also have adjunction from different sides. So left x and left x star are joined from one direction, but if you change the product, the order of product in your category, they will become adjoint for the other direction. So of course I don't remember, this is called this dual is called this thing. Let's assume it's called left dual, and then there is another notion of duality when you require here a junction for the other direction, and then it's called the right dual. And the right dual in a monoidal category is the same like left dual in the monoidal category when you reverse the product. So this is nice, and so if your category is symmetric or even braided, you remember you get all these options. Then left dual and right dual are isomorphic. So if it's symmetric, and then or if it's braided, then they are isomorphic, but then you have two different isomorphisms, the braiding and the inverse of the braiding. And if it is symmetric, then it's two different isomorphisms also. Okay, so this is one approach to duality. Now, another approach, I somewhere got the feeling that this other approach kind of requires the category to be symmetric, or in order to be equivalent to the first approach, but after I thought about it, I think it's not true. So I think what the other approach can work in general, and so I will tell it. Then, but take it with a little star, maybe it's equivalent only under some assumptions like symmetric. But I think if you do it right, so what is the other approach? The other approach is via internal home. So you probably remember we talked general about internal home, but we talk not about something specific, well defined, but some philosophical things. That sometimes you have, if you have forgetful functor to set, and you might have an internal home functor that might make sense. But in monoidal categories, you can actually define it as a well-defined thing. Because what is the idea of internal home? We want a map from x to y, and we want to understand what is a collection of maps from x to y as object. And as usual, we can do it using Unidell's lemma. So we don't really know what are maps from x to y as object, but we know what are maps from z to the collection of maps X to Y. What is this? It's kind of bilinear map, by map, something that for any element in Z, I'm still talking intuitively, gives you a map between X and Y. So for any element in Z and any element in Y, it will give you an element in Z and X, it will give you an element in Y. So what does it mean? That home between Z and the internal home, so internal with curly H X to Y, should be a bilinear map from Z and X to Y. So in general category, there is no such thing as bilinear map, but this is a monoidal category, and we know linear algebra will take the tensor product. So we want it to be in home of Z times X, and this we can kind of use as a definition of the left-hand side, modulo the LLM. And another way to phrase it is just to say that home is right adjoint to Lx, to R. Home from something to Y is right adjoint to R home from X to Y. No, sorry. Home from X or something is right adjoint to Rx. This is adjoint to this in this order. I hope I did math science. So in any monoidal category, we can try to define an internal home as a right adjoint functor, and it might exist or might not exist, but if it exists, it's unique. So it's conditional even on single object X that there will be an internal home from X to something, and in order for X to be dualizable, a necessary condition, not sufficient, that there exists an internal home for X. And then you can always try to define the dual. You can define X star to be internal home for X and Y, like you usually do when you do the duality. But so you can say that whenever X has internal home from it, we say that X is dualizable and this is a dual object. And it's okay definition, but it's a much weaker condition, so it's kind of very weak dual. For example, in vector spaces, any vector space has this weak dual, just you have internal home in vector spaces and home to one is indeed a weak. But this is not a strong dual, so duals that have evaluation, co-evaluation, etc. in vector spaces, you already have for fine dimensional vector space. So not here. And then what we do when we want to so we need to impose additional condition when a weak dual is an actual strong dual, and we know how to do it. So because now we have X star, and we have the functor Lx star. And Lx star, now we have morphism from here in the internal home of X. And this is rather easy to check that you have such a morphism just because of the definition of internal. And now you can ask this morphism to be an item. And this would make a weak dual to be a strong dual. And you see it in vector spaces. So you have home from a vector space from V to W, yes, internal home. V to W. And you have V star tensor W. Yeah, you see that each time you have element here, so you have a map like this, each one. But this map is not an isomorphism. This exactly will give you a finite rank morphisms. Morphisms with finite dimensional image. Yes, because morphisms which are finite combinations of functional times element in W. So each pure tensor here gives you a morphism with one-dimensional image, and when you take finite combinations, because this is finite combinations of pure tensors, you get morphism with finite image. So sometimes this will be isomorphism, sometimes no, but we always have this morphism. And once you have such an isomorphism, then X have a dual because this functor is left adjoint to whatever it need to be. No, it was left adjoint to Rx. Okay, so maybe I messed it. So maybe this is why they require this metric condition, but you probably can choose things correctly, and then it will be left adjoint to Lx, or adjoint to Lx to one from one side, and then by the previous definition to F, it's a dual. So, any questions about duality? So we make 15 minutes break and duality. Good stuff. I have a question too. So, usually in some courses, I usually try to give for credit on the same schema a task to write something in Wikipedia. This time I didn't do it because I had this feeling that everything is very well documented in the web, but maybe it's not really correct feeling. So maybe not for credit, but do any of you want to take one of the topics that we discussed and write Wikipedia article in Hebrew or in English, depending on what language you prefer to write in, and I can type it.
Maybe.
For example, you complain, I think they also saw that there is no good article about whole limits or the limits of categories, because when you Google limits of categories, the
Yes.
definition of a limit in a category, which is completely different.
Yes.
Yeah, probably there is an article about whole limit and limit in two categories, but this is kind of overkill. So, and we want to make that.
By Wikipedia, you mean Wikipedia or NLog?
So I thought that everything like in the union of those two things everything should appear, and I think it is not there. So in NLab you will have limiting between category and into category. Okay, but if I want the more concrete thing, I will see it, but it's a special case of something very general. And if I add Wikipedia, even in English Wikipedia, it still says okay, oh. In Hebrew side of them. But in Hebrew, there are lots of things that are not enough. If you were quite in Hebrew, you mentioned things. And it's simple thing that and just translate and change from the English and take it ahead.
No, I was wondering how useful are Wikipedia articles in Hebrew about advanced math?
So I think it's more question to you than to you.
No, I think it's more of a question to you.
So for me, it's a big difference.
Do you actually
But
read
I'm not in the
Wikipedia?
quality generation. If there is Hebrew, I prefer Hebrew. Now there is ChatGPT, I can ask him to translate, but it doesn't do a very good job. So it can be a way to write the article, but you need to work on it as well. But I'm not in the quality generation. You are for quality generation. When there is an option to Hebrew, you prefer it. And for you also. So for you, it's not good.
I guess there are people who prefer Hebrew.
In my generation, there was lots of people.
Maybe it's been conditioned to first look at the English because it's
More fun.
yeah.
And for you, like reading in English the same as Hebrew. Well, you can more people from the generation.
można gdzie ma krótko.
Ты спрашиваешь по мероприятию права или по мероприятию, что просто
Помню, что
да.
они просто взял и сделал из... То есть дифференцирован, дифференцирован. Раньше было могло стоять сам правильно поступать туда. Но я себя сказал, за счет того, что
Да, я хотела
он
сделать
что
для одного. Можешь спросить? Если не хочешь. Да. Я немножко. Я обычно лучше всего получу курсы проектом.
теория кажется. Господи, появился, я уже стал проверять.
Нет, это что здесь не подходит. Huh?
Okay. So, and now, a nice thing about monoidal categories is you can discuss three monoidal categories generated by one object. And then you can try to replace it. So what do you mean by three monoidal categories generated by one object? And usually was to define no, take them off. With initial object. So to do it formally, you need to talk about initial object in a two category. But it's not very complicated, just do it in both cases. So what does it mean for monoidal category generated by one object? It means a monoidal category C with an object X here. Says that for any other monoidal category C prime and object X prime. I want to say that exists and unique a monoidal functor from C to C prime that maps X to X prime. So of course it's not true, there are many such monoidal functors. But the category of all monoidal functors from here to here, I want it to be a trivial. So any two monoidal functors from here to here are uniquely asymptotic. So if you just consider monoidal categories, this is all stupid. Stupid things to do. Serious thing to do because you basically, so this free monoidal category generated by one object is kind of meaningless thing. So you have this object X, you have trivial object 1, you have X tensor X, etc. So formally speaking, you have many other objects because it's free. So you have X tensor X, and X tensor X, for example. And in the free world, you would assume that they can be different, but you know that there is an associator between them. So you could have hoped, okay, there is one associator, but maybe they will give us non-trivial structure. But you know that everything you can do with many associators, for example, when you have 4 objects and you have many associators, yes, you will get somewhat of a freedom of product of 4 objects, but it has to be trivial because of the pentagon diagram. And you know that in fact, so I think Vladimir talked with you about it, so for larger number, so then you could have add more and more pentagon axioms. You don't really need to add them because they just no, it's not pentagon. It would be a very complicated graph, but they locally look like the pentagon, so they're all commutative there. In fact, you have polytopes. Yes, for 5 objects, you have polytop of different ways to put the parentheses. Yes, so you have exclude 5. There are many ways to put the parentheses, more than 5, and but there are in chunk of 5, so each time you have. Sometimes when you change parentheses, you just if two objects are constantly together, then you're in fact in the situation of a 4 objects, and then you have pentagons, so you have a big graph, but there are pentagons on this graph, and in fact it's just a polytope, and the pentagons are these faces, so I would guess it is, maybe I'm wrong, I would guess it is the decaedron, so there are 20 ways to do it. This all the other
squares.
What?
Actually, also.
Are you also squares?
So
it's not the decaedron. So some polytope, and the fact that it's commutative diagram, you can just check locally, so you have no any new information. So just free category generated, monoid category generated by one object. The categories objects are just integer numbers, because all these guys are the same, so just you can call them x to the n, but they're indexed by n. And the morphisms are order preserving maps between. I don't know, you don't just you just don't have morphisms. Because you don't have morphism from the unit object to the object, so just no morphism. So it's very strict. But once you put additional structure and additional conditions, then you start to get much more interesting. So the first thing that you can do, you can put braiding. And then suddenly you get much more interesting category. The category of objects are integer numbers. And morphisms, so they're only the 2 points, they're only isomorphisms, so the integer numbers have to be the same. So what are the automorphisms of the same of the number? Do you have a guess? So what is a free braided monoidal category generated by one object? So let's see. You have x times x and x times x. What are the morphisms that you have to have between these two things in any braided monoidal category?
Power supreme.
You have the braiding. And once you have the braiding, you have all its powers. So the collection of morphisms is going to be Z. Okay, not very interesting, but already we started something. What happens when we do x to the third to x to the third? Ignoring the associator because just don't give anything new, so I just fix x to the third as one object. What things the braiding gives you when you do like this? You know the answer?
Yeah.
Anybody else know the answer? So yeah, what's the answer?
It's a great group of 3 grades.
The group called BISU. You see, I will discuss it with you. So it's groups that you can describe geometrically like this. You have 3 points here, 3 points here. And then you do passes. So you can think that you're working in R3. And these 3 things are on the same plane here, and this on the same plane here. And then you do passes. I draw them on the blackboard, but they're in R3. But they always have to go downstairs. But they cannot cross each other. But they can on the plane they can cross each other. So in R3 they don't cross each other. No. Some weird thing like this. So in R3 we will draw them like diagrams like this. And this is called the braid group. So there are 2 descriptions of the braid group, one topological description. And so basically it's pi1 of a certain topological space, but you can say more down to earth and just passes collection of n passes going from n point here to n point here. Each point is some point in the target. And they are not allowed to cross each other, and they have to go down all the time. And you consider them up to home in this collection. So.
Yeah, but I'm sorry, but this is exactly a path in some topological space.
Yeah, so it's also pi1 some topological space, but I want to say it without describing this topological space like this. So this is one description, it's already 2 descriptions like this, and then closed loop in some topological space, but I don't want to go there. But also there is a combinatorial description, like Sn. Sn have very, so you can consider that permutation, which is also kind of combinatorial, but it also have description with generators and relations. So the generators are flips of two elements, and the relation is that when you do the flip twice, you get identity. And then there is funny relation when you have Si I plus 1 and S I plus 1 I plus 2. So you probably remember there is some relation between these two transpositions. The one, the second, and the other way around, you get at some point you get identity, I don't remember it. And this is sometimes called the braid relation. And the braid group is generated by the same elements, but without the relation that when you do the twist twice, you get identity. And the idea is that you can do like this, the twist, and then do it again. How do we do it again? This goes from above and this from below. So you do it like this. And this you see that on the topological level it's not the same. You can't like tell them apart, yes? So it's not equivalent to this. And so you don't put this relation. But the braid relation basically says that you can go from below like this. Or what is the other way to do it?
The braid relation is cubical relation.
What?
It's cubical relation, so you need three crosses.
Okay, so I don't remember it. But you can also draw it and it will be something rather obvious. Obviously, the homotopic. So it is a relation. And of course, it's very non-trivial to show that the two descriptions of the braid groups are the same. So it generates some relations for one side and the logical for the other side. I can say the general method how to do it. So you see it very much in knot theory or any low-dimensional topology and even non-low-dimensional topology. So the first thing that you say is that we define the braid here in R3 because we want to draw it on the plane. So the idea is that any drawing on anything on R3 you can project to the plane, and with probability 1 you will get only reasonable intersection. You will not get triple intersection. You will not get like simultaneous intersection different things. And each pass will be smooth pass. It's not obvious because if you have smooth pass in R3, if you look at it from a very bad angle, it's not smooth anymore. But with probability 1 it is. And the correct way to say probability 1 in this case is Start's lemma. So there is Start's lemma which allows. And then you say you give one direction that any braid is represented by this combinatorial braid, some that you say, okay, I'm going down, then I interchange these two guys, I interchange these two, then interchange these two but from behind, then I do something else. So any braid can be described with the generators. But then the question is why so then you have to prove that the relation satisfies. This is easy because you just do it topologically. But then you can ask why you find all the the relations. And this is much harder. And the idea is that you say, suppose that the two things are homotopic in R3. So homotopy in R3 is also some surface, yes, in R3. Then you project this surface to the plane. And again, with probability 1, but this is much harder, when you project it to the plane, you generally get some homotopy inside the plane. But not always, because the probability 1 doesn't work this way. Sometimes you will have collusions. Sometimes you will get things that in the plane doesn't look like homotopy. So for example, if you have this thing and this thing, this is the same as this thing. But when you do them, you see on the plane you don't have homotopy. So this you have intersection here with the plane. So something changed. And so the combinatorics change. But again, when you do everything too generically enough, you can have some control about what shapes. So no triple collusions are not like complicated things that happen. And then you try to analyze what happens in these bad points which are not very bad. And you see that in each bad point you basically get one of the relations. This is not proof at all. This is like the general schemes of all this proof. This is a hard theorem, but it's well known as this not theorem. So another version of this theorem is a theorem about Rademacher moves. I don't know you heard Rademacher moves? This thing is called Rademacher moves. So you have knots. You know what are nodes, yes? Node is a continuous map, continuous one-to-one map from S1 to us up to. I say continuous, but it's very easy to see that any continuous map is homotopic to a smooth map. And if two maps are continuously homotopic, then they're also smoothly homotopic. So we can say smooth maps. And then any node you can represent by its node diagram. When you draw a node on the blackboard, you don't have R3, so you draw diagram. Yeah, so the most known one is this one. So this is not diagram because we don't see what I'm doing here. It's overlap. But then I'm doing that. מעל, מתחת, מעל. This. And then you see what's going on. And again, how you do why any node represented in node diagram. And very simple, or not very simple, but relatively simple, you project it to a plane, and generically all the intersections will be nice and smooth, and then you only need to record in each intersection, there are no triple intersection, who is above and who is below. So yes. But then you can ask whether two nodes, whether two diagrams represent the same node. And of course, sometimes they're just homotopic as diagrams, you can, I don't know, draw things like this, or this is stupid, the homotopic diagram. But there are non-trivial things that you can do, like here, yeah. If you have pieces of the diagram that look like this, you can change it to pieces of it. And this is not trivial at all. And the idea is that you have yes, so you have this Rademacher move, so some collections of non-trivial things that you can do, and that together generates all the equivalents. And in order to prove it, you use the same argument. And it's not trivial argument, but it is not. Okay, so the braid group, the braided category generated by a single object is this very nice topological category. So it's easier to prove that the combinatorial description because you just have the braid relation just becoming one of these diagrams. You remember hexagon diagram or one of the diagrams, and then you just see that there's a free group generated by this relation, just the same like a free category generated by one object and the braid orthorhomizism. It's harder to prove that the topological description is correct, but you just prove that the topological, the combinatorial. And what is a symmetric monoidal category generated by a single object? This here. Any guesses?
The symmetric one.
What is a category?
And the permutation one.
But what's the actual category? You of course write your answer, but just what are the objects of the category, what are the morphisms?
The objects are the same multiplications.
X
Like
to
it-
the n, just numbers and
Like,
morphisms.
yeah. Well, from x squared to s squared, you have two.
You have two, you have S2, and in general for Sn to Xn. What are the morphisms like this? So it's a groupoid of finite sets, objects of finite sets, and this is then the product of this John. Okay. And this works. Now what happens if we want a free rigid category with dual? Free monoidal category with dual. So if we just want dual but no braiding and nothing, then again it's probably not that interesting. I didn't think about the answer, so I postponed it, but it's not that interesting. But once we put braiding or we put symmetric structure, then we get much more interesting objects. So let's start with symmetric. So what is symmetric? Rigid monoidal category generated by one object. any object. Any guesses? No guesses? So what are the objects this is? We still have x to the power n.
You also have an X.
Start with and assumption. What are the morphisms?
And here is not real.
Is even better, it's meant.
Oh,
If it's not braided, then you have a lot of words like this, but very small amount of morphisms. I don't know from
we know that we have the action of Sn and S7. These options.
yes. But we also have now it's not true anymore that all of the morphisms are isomorphisms.
Also, we have units of quickness.
Yeah, so I can tell you the final answer. It's not so simple. X to the power k or n1 x star n1. So what we need in order just to have an morphism, we need some condition. So the condition is not that this equal to this and this equal to this, but that this minus this plus this minus this is equal to 0. Yeah, so it's okay to have more this, but then we have to have less this. Why? Because we have the unit and the unit. And what are the morphism? So what another way that this plus this is the same like this plus this. So the morphisms, you can say they just bijection between this set and not all of the morphisms, but some of the morphisms are bijection between this set and this. But how do I want to do it? So to each copy of x, I will put a point with a small arrow downstairs. And for each point of x star, I will put point with the arrow upstairs. And here also, downstairs and upstairs. Oh, we need one more, yeah. And then I want to connect all the dots. Not in topological sense, just combinatorial. I just want to say who goes to who. But I'm allowed to connect like this. This is a unit, I think. I'm allowed to connect like this. This is a coin. And I'm allowed to connect like this and like this. So, but the arrows should be compatible. So the direction should be. So it's all diagrams of this type. And this is exactly like bijection here.
And also all brain.
No, I'm now in symmetrical. I'm normal, okay? But I also allowed to do something completely stupid. I can take.
I'm sorry, so you allow crosses.
Yeah, I just doing it combinatorially. Yes, I just say who goes to who, and I completely don't care how it goes. I just need to pair them. I draw it like a diagram, but I think about it just pairing. So just as a mapping for the union of these two sets to the unions. Because each point here can be mapped back to here, but to X star. So it's not really mapping, it's just a co-unit. Or unit if it's upstairs, co-unit upstairs. But also I have a stupid thing that just taking co-unit and then the unit. So identity object just represented by the empty set. And co-unit will look like this. More like this. And then the unit will look like this. So it can erase these arrows and just consider it as a loop. So I just can like put several loops here. It's something that I'm allowed to do. Yeah, so the loop I can call it some element t and just can take think like this and multiply it by t to z. So it's these are the maps, but I also can multiply them by. I call it multiplication because when it's automorphism, it's actually multiplication. And how do we do compositions? So we add the powers of t, we have several loops, and we compose this diagram of this and correspondence. Okay, this is already nice, but it's not very interesting. So you get much more interesting picture when you go to braid. So what is braided, rigid, monoidal category, free braided, rigid, monoidal category generated by one. Any guesses?
It's
What? Tangles. So yes.
program.
So you still can describe it on the level of diagrams. So the objects still look the same. Some looks up, some looks down. And the morphisms are drawings like this, but these times, each time you intersect, you need to specify how you intersect, going from up or down. And you can also now have some interaction with the loop. Each time you have a loop, you also can go up and down.
Can you explain why?
So let me try. I want to finish this the story and then try to explain why. So first of all, I want to describe what. So you can do such diagrams, and in these diagrams, you're also allowed to go back and forth. You don't have to go always down, because once you have co-unit, so unit is thing that looks like this, and the co-unit is thing that looks like this. Yes, so unit have two errors. So you compose things in your morphism. So unit, you have x times x star maps to identity. Identity is empty set, so you have to connect them with this. So you can go up, you can go down, you can go above, and when you intersect, you have to decide you go above or below. And this is called tangles or entangles. The category of tangles. I will say what are tangles in a minute. And as a category, this is called category of tangles. And this category, maybe I want to go to the previous example. In the previous example, I can ask what are automorphism of the trivial object in the symmetric case. So what are the automorphisms of the trivial object? In the free symmetric monoidal category generated by rigid monoidal category generated by one.
Sorry. Respond.
Yeah, it's a unit object. It corresponds to the empty set. Yes?
Yeah, but I think now it's called links.
Yeah, but I want to talk about the previous example for a moment. It's easier.
Projections of links.
What?
Projection
Yeah,
of links
but let's see what is here. Don't go further. So we have empty set, so no errors, no strings like this. The only thing that we're allowed to do is loops. And we just can do 1 loop, 2 loops, 10 loops. So we just do this semicolon and just conditions. No, it's that because the loop can go to, right? Yeah, it is because it's symmetric category, so you can do it from two sides. You have so you answer. Because each time you do loop, you can do it like this, or you can do it like this. And these are in general different loops. Yeah, pretty sure. Do I see why the compositions of these loops is identity? I'm not sure. I'm pretty sure it's.
You have to take the. Well, how
No, sorry, not that. No, I'm taking my go back. I will check it. The next time I want. Yeah, it's
evaluation, right?
yeah, evaluation is not co-evaluation.
so
It's called co-evaluation is composed with evaluation. And this is the
Yeah, so you get n, but you don't necessarily get the.
Yeah, you don't. You have also less, you have like 2 evaluations because it's symmetric category, but I don't see the evaluation. I will check, but I think it's just. But here you get much more interesting thing. What is the automorphism of the trivial, the unity object here? So we already say that. So you do tangles like this, like you do these drawings, But there are no passes going from up to down because there are no up and no up, no down. Only loops. But these loops can still go above and be below
So
each other.
these are not.
They're not exactly not because you have more than one loop. Even one loop becomes very non-trivial thing. It's a knot. But you can have many nodes, and they also can touch each other. No, not really touch, go above and below, so they're linked to each other. For example, you have this node. Above and then below. Okay. So this is this. So this is a link. So link in general is a union of nodes in R3 up to homotopy, which do not intersect each other, but in the homotopy also not allow them to. So this is the same group because there is a empty link and you can add link to it, put them aside and take the union, and they are oriented links. So each time you have also arrow saying how you're doing it, and so you get a collection of all oriented links, and this is the same group. And very non-trivial same group. And you got it like kind of for free. You started with a free monoidal category generated with one object and free rigid breaking. Okay. And nice things that you can get out of it are, at least theoretically you can try to get out of it, are not invariants. Because now suppose you have some specific monoidal category, braided monoidal category A, and some specific object X. And you have this free monoidal category, let's call it the category of tangles. So because it is free, you always have a functor from E to A that maps the trivial object, the generated object here to the generated object in B. And now,
A again?
what?
What is A?
A is some embedded monoidal category with one rigid braid. And then you can ask where this so the end of freedom of identity, or the auto freedom of identity here, or end of freedom of identity here, goes to end no freedom of the trivial object, the unit object here. So any loop, any link, sorry, give you a number here. Oh, not a number, element in end of the trivial object, which might be if you are in linear, if you're in additive case, it will be a big group. If you're in linear case, it will be a vector space, and often it's just a base field. So you get invariant of links, which are kind of numbers. Not necessarily numbers, it can be rational functions, polynomials, etc. But they want to be numbers. And theoretically, it's very nice. Practically, it's not really easy to explore because to construct. So if the category is symmetric and not braided, and not just braided, then it's kind of stupid. Yes, because then it is not invariant, a linked invariant, but it factors through the stupid invariant of like tearing everything apart and taking lots of circles. So that it's not interesting. So to construct non-trivial braided structures, it's not very easy. And each time you do it, you can construct an invariant. And I think the most famous thing is the home fly PT polynomial. So home fly PT is the initials of the 8 people that got credit for doing it. So some people use not the entire name but shorter because they was not aware of each other. But I think this is like the most fair and complete description. So this home fly PT polynomial that can be really described in this way, but to construct this monoidal category, we'll try to discuss it. It's much harder than just to construct the invariant. So yeah, we will discuss it, but kind of application of the theory, but more like give you motivation to do stuff than actual application. So what are tangles in general? So in topology, tangles is things like this. So one definition, you take the sphere, you take n point in the sphere, and then you take topological spaces or passes or union of passes that connects. So you have to take even number of points in the sphere that connects all the points. They all have to be inside the sphere. They connect all the points in the sphere to one to another. So no, there are no triple intersection, no intersection at all, and all the points are connected. And also you have links. So also you have some. So this is general tangle, and then there is a notion of oriented tangle. So oriented tangle, you have two endpoints, but now they're coming with arrows, some of them going inside the sphere and some of them going outside. And now you have to connect them, but only inside have to go to outside. So you have to be compatible. And also you have links, so also you have some loops that they also have to be oriented. And now what is the category of tangles? And the category of tangles is the categories whose objects are like pair of integer numbers, so you can consider them as points with arrows. Some go up, some goes down. And morphism between two such tuples, so you put one tuple on the upper hemisphere, as the other in the lower hemisphere, but the rotation change. So if this go up, so in the upper hemisphere it will go outside the sphere, and in the lower it will go inside the sphere. And now, in order to have at least one morphism, the total number of outside going arrows should be equal to inside going arrow, and then you draw the tangle on this. So this is a category of tangles, and in this category, the automorphism of the trivial objects, that empty set, are exactly these. So the tangles without not touching this. Okay, now when you ask why all of it is true. So as usual, to show that the topological description is correct is hard. And to show that the combinatorial description is correct is not that hard. So why is the combinatorial description, or more or less why the combinatorial description is correct? So we need to frame the combinatorial description a little bit more accurately. And what we actually allow to do. We said that we allow to connect points here to points here. And we can do whatever we want, but we need to do it kind of discretely. So each time we have many stages, and each stage we can do one of the following things. If we have at the beginning of stage 2 points, then we're allowed to do this crossing. Of course, we're also allowed to do the opposite crossing. Yes. And we're allowed to take out of nowhere and put such an out. And if we have 2 points in the beginning, we're allowed to add an out axis. And this is it. And this thing that we're allowed to do. And now we have to put equivalence relation. And the equivalence relations are exactly the braid axioms and this sometimes called, okay, let's phrase it. So you remember the axiom with the zigzag axiom, or I don't know how Shachar called it. So let me go with now. What is written here? This represents the object X, yes? This represents the trivial object, so we have X and 0. Now, here we have X, then 0. I think this is X star. And here, this is identity tensor the counit. Because here also X next.
Shouldn't it be
I did it
one
only.
goes to X?
This is super. Oh, no problem. Now what we have? No, I don't want it. No, I want. So probably the other dual. Left dual and right dual. I want it. Now we put. Yeah, maybe I don't want to draw it like this. I want to draw it this. So this first map is just adding the trivial object here. Then you do this. Okay, then you use associator. Here. In the diagrams, we don't do associator. And here you put the unit. And here you put. So this drawing, if you define it like you do it in stages and you draw this drawing, corresponds to this combination of braiding and associator and the unit and the coil. This is the unit.
And about the top drawing, when you have two lines, what does it correspond to?
What?
Well, I'm kind of confused.
This is the braiding. This is the opposite braiding. This is a coil unit, and this is a unit. And all morphisms in the free category have to be written as a combination of these guys and the associator with braiding option. Yes. So, and here you just see each drawing when you do it like actually, in order to the drawing will present some specific formula, you can't just doing I don't know, like here, like you need to do it accurately, so you allow only these bits. Like suppose you're doing it in a computer, but in pseudographics, you cannot just draw pixels. You work in a grid, and each square in the grid can be one of these three guys, and they all have to. Yeah, you can do it like with a card game. Suppose you have tiles, and in each tile you have this thing, and then you can use this card game in order to construct a tangle. And different combination of cards a priori give you a different morphisms. And then this morphism is kind of very different from the morphism. But of course, on the topological level, you see that these two things are equivalent. And as the fact that they're equivalent just is a snake lemma. So you can say, instead of just saying that you consider diagrams up to topology, you say you consider diagrams up to some very specific set of manipulations that you're allowed to do. And one of the manipulations will be the snake lemma, and other manipulations will be the braid, braid axiom, so I think the hexagon axiom. And okay, the associator you usually don't need because the diagrams are already there. The objects are just x to the power n, x star to the power k. So this is another combinatorial description of the tangled category. I think it's another name, but I don't remember it. Maybe power category. So the objects are points with arrows, and morphisms are these tiles, these three tangles that you can draw with tiles, and the equivalence is generated by some simple operations. And then the hard part is to prove that this thing is equivalent to the topological thing. So the strings are whatever, the relations are whatever you can get with the model. The easy part is to show that any tangle can be realized in this combinatorial way, but the fact that you don't, and all the relations are of course topologically justified, but the fact that you don't have more relations is much harder, and this is proven using the same. Okay. So, we discussed the rigid. Okay, the next thing I want to discuss maybe next time, I can start now, is what happens if you mix this theory with abelian categories. So you can ask, is that your category will be abelian and monoid. So this is usually called tensor category. So of course you need some interaction. So you want that the tensor product will be at least an additive functor, and usually you ask it to be exact functor. And under some, so if you have duality, then under some weak assumption, if it's additive, it's already exact. And then of course you want the this is all the thing else. And now the first thing that you can try to do is consider the unit object and consider its endomorphism. And its endomorphisms in general are from algebra, yes. You can compose them, but also it's an abelian group, so it's an algebra. But if your category is abelian, then each endomorphism can have a kernel and co-kernel. Now, the kernel going to be some sub-object of the trivial objects. And often you want to ask the trivial object to be simple. Yeah, kind of, if it's not simple, then you can take a smaller category. Like the unit object has a sub-object, so it's kind of idempotent, or at least often it is idempotent in your category, so its square is equal to itself. So you can take its product with everything else and just reduce your category. So usually require that the unit object will be simple. And once it is simple, all its automorphisms cannot have a kernel, because if it's have a kernel which is not zero, it's a sub-object. Or it can have a kernel, but then it has to be the entire C. So it means and for the same reason, it can't have non-trivial co-kernel. So it means that any automorphism with a trivial object is either zero or invertible, which means that it is a skew field. The ring of automorphism of the trivial object becomes skew field. Often you prefer to work with field, so you just put another axiom, you want it to be a field. And I'm not sure. Like a field, but without commutativity on the bottom. Like a term, for example. But often you don't like it, so you require it to be a field. And then once it is a field, all the home spaces, you can multiply them by elements of this field. Because from x to y, but x is the same like x times identity. And not isomorph. So, and here you have automorphism of multiplying by automorphism of identity, or endomorphism of identity. So everything becomes linear space over this field. So your category is K linear. So you have some base field, and the home spaces are K vector spaces. So often when you do tensor category, you just say we will fix a field K in advance. You postulate that the automorphism group or endomorphism group of the trivial object is equal to K. It's not just some field that includes K, it's equal to K, because if it's larger than you, will just change the definition of K. And now it's K linear category. And what is the best example of K linear tensor category? So for symmetric, in the symmetric world, for symmetric categories. So one of the best examples is the category of representation over K of a finite group G. And this is a tensor category, it has a duality, with a finite dimensional representation. So a finite dimensional, so you have dual representation, you have tensor product, and then you see. Some other examples, a little bit more careful, complicated. The same, but G is now replaced with a profile. Yeah. Do you all know what are profile groups? What? Yes, what so I'll answer the question. And so this is one direction to generalize, another direction, algebraic group. Right? G will create algebraic group. Algebraic group, if you remember, is a group object in the category of algebraic group. And in fact, you can mix these two examples and get pro-algebraic group. I will explain what this next time. And this is a very general example. Finite dimensional representation of a pro-algebraic group. It's not all the tensor categories in the world, but if you put some reasonable conditions, then you get something that calls the Lacan category. Then the theorem, like Naka, that saying that category that satisfies tensor category is this additional condition, that the Lacan condition is equivalent to the category of representation of a pro-algebraic group G. So this is what we will discuss next time.